All right, so we will start. Good afternoon. Today's topics are on the screen, as you can see. We will do what are somehow a little bit more naive, some simple searching in an array when conditions are nice. That means when somebody prepares you nicely data, then you are able to search in them efficiently. So that's the upper part of the slide, and the lower part is concerned with the situation when they are not that much nice and when they give you just some data and you have to cope somehow. So first, let us start with searching in an array. First of all, if you are going to search in an array, what must happen before you go searching is that your array is sorted. If the array is not sorted, or list, or any kind of more complex container or data structure, then you have no other option than go one after one through all the elements until you find what we are looking for. If, on the other hand, they pre-sort, or they you the values, then you can say, all right, again, you can either go searching as you did before, step by step, as the middle part of the slide shows you. Start at the beginning, what are you looking for? 993. So then you go one after one, and finally you find it. Of course, it takes a rather long time. Of course, you have to scan the whole structure. You might be lucky, on the other hand. So if you adopt an optimistic view, then you might say, okay, sometimes we might be lucky, so it's kind of lottery, so let's try, maybe we shall win. As in lottery, you will not win that often, of course. So that's a standard naive search in an array, and it is slow. So instead of that, you typically apply this so-called binary sort, which behaves in the way probably known to most of you. I will just repeat it. So what you do, you are looking for some particular value in your sorted array. So what you do, instead of looking for that value, you jump right into the middle of the array and check whether your query, let's say, the data you are looking for, whether that data is bigger, or if it is bigger than the element which is in the middle of the array. And there are just two possible outcomes, yes or no. So in this case, the answer is yes. So you say, so everything, including the queried element, is surely there in that part of the array there will not be your value you are looking for. So you are left just with 1/2 of the array to look for your data. And so when you are left with only half an array, then you say, all right, you can recursively adopt the same strategy and say, well, we continue in the same fashion. So go jump into the middle. What's there? 939. So you compare your value which you are looking for with that value in the middle. And again, it is one test. The outcome is no. So you just cut off the remaining part of the array, and you are left with, again, with just more or less 1/2 of the previous half, so with 1/4. And so you continue until you come to a situation when the part of the array you have to explore is just one element long, and only then you will check whether that value is equal to the thing you are looking for. You might say, well, you might say that maybe this is not that efficient, because during the search, in fact, you have found that encounter. You have not found it. You encounter 863 even earlier. So maybe it would be more efficient each time when you arrive to some middle element, maybe just also check that element whether it is equal to the thing we are looking for. But that's not, strangely enough, that's not the case, because what's happening is that you just lose time. Typically, you would lose time by checking those elements which are not equal to the query. So as you can see, the next slide tries to explain it in more detail. Typically, if you find a value you are looking for, you will typically find it later in the search, when you are quite close to the end. So if you are in each stage of the search, if you are also checking those values, those intermediate values, whether they are equal to your query, it takes some time, and you will then just spend two tests here, two tests here, and you may now imagine that there are more lines if the data are bigger. So typically you would spend more time. So imagine your array is let's say 1024 elements long. So then you go searching, and your array is getting smaller and smaller, or the piece of the array where you are searching, 512, that is 256, this is 128 long, and so on until you arrive to size, let's say 4, and you arrive to size 2, and finally you arrive to a size 1. There is your query Q, which is equal to I don't know what, and then that Q is sitting exactly in there somewhere. So during the search, you would check here, that's the middle, so there you would perform 2 tests, and then there where they cut it off, there you would perform 2 tests, then here you would perform 2 tests, and so on. So at most, this is 10 to the power, this is 10 to the power of 10. 1 is 10 to the power of 0. Of course, 2 is 10 to the power of 1. So you would do at most about 20 tests, because you will perform 2 tests on each line. So at most about 20 tests, and it is obvious when you are looking for your query that the probability that you will find it early in the search is quite low, because the data are big and you just choose one particular position in those data. So at most about 20 tests expected, probably nearly the same. Same, that would be about somewhere 17 to 19 or something like that. If on the other hand you perform only 1 test on each line, just checking in which part your query is, so you will perform only of course 1 test here, 1 test here, and so on. Therefore, if you do 1 test, then you have to get to the last piece of the array, which size is only 1. So there you must perform perform at least 10 check, not perform 10 tests to shorten the part of the array you are looking for, you are using. So the test to shorten the, let's say to shorten the array, or to shorten the area. And you are checking, so you must perform those 10 tests plus 1 at the end, because you at the end just check whether your element is whether it is really the thing you are looking for, because it might not be there, of course. So that total is then you perform 11 tests when your size is, for example, 1,000 plus. So it is not worth checking. It's not efficient to be optimistic and expect that the best will happen soon to you. It will not. Therefore, we can have the easy, I think it would be easy code, but before we look to the code, here they just remind you how long does the search takes in general terms. Typically, if you take this example and you say, well, my array is big, like, for example, power of 2, then, of course, that power is proportional to the number of steps you have to perform and to the number of tests you have to do, and therefore, that number of steps is equal to binary logarithm of n. So just to remind everybody how big those numbers are, let's say, so logarithm 2 of 10 is 3 point something. I don't know how much. What is then important that binary logarithm of 1,000 is more or less similar to binary logarithm on of 1024, which is 10. So that's about 10 logarithm. Therefore, if you multiply 1,000 by 1,000, I mean 1 million, of course, is the sum of logarithms of 1,000, which is then 10 plus 10, which is about 20. And again, if you multiply the argument by next 1,000, by another 1,000, you will get 10 plus 10 plus 10. So the binary logarithm of 1 billion is about 30. And therefore, you know that if your array or your list where you are looking for a particular element has 1 billion elements, so it takes about more or less whole your memory of your machine, then you have to perform about 30 tests, which is very small number compared to the size of the data. So it is very efficient. That's why they show this bright face with a light bulb on. The code is, again, very simple. What you do, you search in your array, and you give them value you are looking for, and you do the following. You say, okay, let's take the first element, let's take the last element, let's take their position, and of course jump into the middle. So you start with the beginning, at the end, and jump into the middle. What does it mean to jump into the middle? Just take a arithmetic mean of these positions, and then you just check whether you have to go to the left or to the right. So it is exactly this check, whether the element in the middle is smaller than the value value you are looking for. If it is smaller, then you just neglect this part. So in that case, your beginning is shifted to the right, and your end remains the same. So the low part now shifts to the mid +1. Therefore, you are left with this part. If this is not true, then you are considering only the left part, and that this means that your upper index is shifted to the right. So now this last index becomes equal to the middle one. So, and there is a loop which says do it as long as the segment length, as the segment we are investigating is long enough to be able to be divided into two pieces, of course. So while the length is bigger than one, and that's it. There's nothing else. So when you arrive to the smallest element, you say, we now just check whether this element is exactly equal to the value we are looking for. If it is, then here they return the index of that element which is there in the array. Otherwise, they return something which surely cannot be the index of that element -1, or you may raise an exception on that. That depends on you. So this is a Python code. So there is no problem whatsoever with calculating with integer arithmetics. There is no problem. In some other languages, there might be problem because low plus high might be this low plus high might just overflow your integer or long integer data type. So you have to be careful when implementing it in some other language, and you expect the data might be extremely big. So that was originally some issue in some version of Java. Then they fixed it, and then they described their experiences here in this link. So we can search effectively in an array, and it is rather effective, as we have seen. It is effective. Now, can we do better? Question is, can we do better? It's always the question, can we do better? Maybe yes, maybe not. People always try, and surprisingly enough, they succeeded. We can do better than this. But again, only in some cases, not always. So sometimes we can do better, and it is in the case when our data, when you expect the data are more or less uniformly growing if the array is sorted. Of course, the method, so-called interpolation search, is not good to use when your data are, for example, very small, like 1, 2, 3. Then suddenly it jumps to 10,000, 10,002, 10,003, and then again it suddenly jumps to 1,403,000. So when it is not very, not too much uniform, not too much uniform growth, then the interpolation search does not work that good. If you can, on the other hand, expect it, and more or less the data are uniformly, randomly chosen, then it's on the other hand much more efficient. There is some quite complicated formula you have to apply. You say and you apply it. So you say, well, we are looking for our query in this segment of an array. So take the first element, take the last element, and just imagine, suppose, which might or might not be true, suppose that most of the values which are between are uniformly getting bigger and bigger. There are no big jumps to bigger values. So more or less the stuff grows as a linear function. If that is true, then you might say, oh, but if that is a linear function, we can interpolate through the first and the last points of the which are on that linear function. And then if you are looking for 939, of course you can expect it somewhere close to the maximum value, which is 993, and small value is 363. So obviously you should be somewhere the proportion of how much smaller is this value you are looking for than the last value. This proportion of values should be the same as the proportion of their positions. So that's what is here in the at the bottom in the formula. And before I again comment on the formula, just look how it works. So you take your query, the value of query and the value of the first element, take these two, compute the difference, which is down here. I have no idea how much is that at the moment, but it is just there. It's just the difference of these two values. And that difference is compared with the difference of the first and the last value. So you've got this ratio, and then you multiply it by the difference between 17 and 0, and you've got something add to 0, and out comes 15.54 in this case. So they expect 939 to be somewhere at this position. So you do not get there exactly, but you get more or less close to the expected position. And now it is again up to circumstances and your approach. If you decide, well, maybe when now we think we are close, so maybe just now look linearly, step by step, to the left, obviously, for the value we are looking for, or now maybe say apply, I don't know exactly what, try maybe some increasing jumps or something like that. So nevertheless, it is relatively close. So you want to do that, or you might repeat the whole stuff again, because now you say, okay, we get to position 15, and obviously our query is smaller than that. So now we can take just this part, only that piece in which our data we are looking for might be stored, and repeat the same stuff again. No one can predict how effective that will be in a general case. There is prediction that this is effective when the data, as I have told you before, are close to linear functions. So let's have a picture. Imagine your data are somehow growing like that, and you are looking for some query, and you want to know where it is located. So you might imagine that there on the x-axis are positions. So there's those are indices in the array: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, and so on. So, and here are, and they are as high as it corresponds to their values. So the bigger the value, of course, the higher is the point. So the last, this is not the last, this is the last, but we are working with just piece of an array, just with a segment. So if there is your first element and there is your last element, so you say, okay, maybe all the other elements follow more or less our linear function, which is given by these two points. And what you do is say, okay, if that is true, which is nearly true, as you can see, or it's nearly, no one knows. So then you say, aha, so then you have this query point, which you know its value, but you do not know its position, where it is hidden in this array. So you go to the, so you expect it to be somewhere, somewhere here where I show you, because what's the math behind the stuff? You say, well, if we know the value of the last element we are talking about, we know the value of the first element in the segment we are studying. So if we know those values, then we can compute this difference and this difference. So we can compute these two differences because the value of the query is what we are looking for. So we can compute this ratio, and that ratio should be the same as the ratio of this line to the of the length of this line to the length of this line, which tells you, okay, what? There are some similar triangles. I hope you can you see them or not? Well, this is linear function. So, if you, for example, if your query is in 3/4 of the whole interval between first and last, then its position should be also in 3/4 of the length of interval between first and last position. Therefore, you might say, all right, so the ratio of this length and this length is the same as the ratio of here, the longer length and this shorter length. So it is exactly what happens here. Q minus A first, which is this stuff, divided by the longer one, which is down there, should be more or less the same as position minus first up there, divided again by the whole length of this interval. So if this is more or less true, then of course what you want to know the position, which is this thing you don't know, and all other values are given. So you just then reorganize the stuff on the right to the formula at the bottom, and you calculate your position just by rearranging high school algebra. That's it. Rearranging this. It's not equality, but you might say, oh, it's more or less equality. So you get the position like that, and that's it. With the position, you again may repeat the search. We have our formula yielded 15. So now you are limited just to this part, and you may repeat the stuff again. So now you calculate that your query should be at position more or less 14, because you are getting closer and closer. You look there, it is still not there. So you might you repeat the stuff again, and finally you arrive to position 13 where you really find your element. So it looks a little bit complicated, and the obvious minus the problem of the method that you have to compute this formula, which contains a lot of calculation. So you have to access the elements of the array and then do the arithmetic operations, and there is 1, 2, 3, 4, 5, 6 arithmetic operations, and 1, 2, 3 times accessing the array. So that's about 10 operations. Once more, 1, 2, 3, 4, 5, yes, 6 plus accessing the array 3 times about 10 operations. So to do one step in the method, you need 10 operations, while in the binary search, while in the binary search you do one operation and very simple operation in each step. So it seems that the trade-off is there obviously big, because we can look at the final results, which say the following. Here is the size of your array. Here is the number of checks in average case when you do naive linear search. That is obviously big. The last column tells you binary search, how many checks, how many just tests it does. So you can see 1,020,000. So that number is very low. And the interpolation method, the number of steps is very low, but you have to remember that each step contains about 10 operations, arithmetic and accessing the array. So it is in fact rather bigger. So interpolation method is suitable when you've got really big data and when the distribution of the data is close to linear. Then of course interpolation method will work nicely. Otherwise, you would prefer, in all practical cases, binary search, because it does its job perfectly and nicely. Excuse me, just to see the interpolation search implementation, again the approach is the same, very easy, while loop which ends at the moment when the first is equal to last, when the segment we are studying contains only one element, then we check whether our query is there or not, and we return either the current position or the -1. So that breaks the loop. Otherwise, what we do, we just apply the formula which was on the picture, and then we decide whether we have to, in the next step, whether we have to study the left part of the right part of our current segment of the array. So there, here we also check whether we already found that element, just additionally, and then of course here is the decision whether we have to go to the left or to the right. So that's about this searching. And now you say, well, that was an easy part because our data were prepared, they were sorted, sitting there nicely, someone sorted it for us, and they are just very static, because if you now want to delete some data or insert some data, the linear array type storage is not very efficient. So you have to go for a so-called binary search tree. So the rest of the talk is devoted to binary search tree. Binary search tree contains, again, it contains some values, and those values we call keys. Typically, in a binary search tree, you store not just the keys which you see in the picture, you also store some additional data. Typically, you store, for example, you store your customer data. And typically your customer data is big. You keep a lot of information about your customer. And your customer, of course, just to distinguish easily between different customers, each of them have some ID of your customers, and that we choose to call also a key. So the ID, which is typically a unique ID of each customer, and then there is a lot of other data associated with your customer or whatever you are keeping track of. Those, and now you store, if you want to search your customers, you have loads of them. So there are lots of these records. So typically you do not store all of them. You don't store all the data in the tree. You store only the ID and the key. You store there in the nodes of the tree, and associated with that node is also a reference to the whole data. So if so in reality, the tree looks like that there is a key, and there is also a reference to the data. To the data associated with that key, with that ID. So there is typically some pointer or a reference. And another key, if you've got another key, 2, it also contains another node, and a reference to the data associated with that key, of course, and that reference goes to some other piece of data in your record, goes to some other customer record. That is what goes. Those nodes, this information represents one node in a tree, in a search tree. Search tree, and what we do not show in all examples are exactly these references. You just imagine that there in each node you can see on the picture there is its own reference to particular data. So customer 70, there is hidden and not seen reference to the data of customer number 70, but we don't include that in the picture because that is not important from the point of view of how the tree is manipulated. You know that there associated with it is always a reference to the data. The data are sitting somewhere else in the database, and that's it. So once you access a key, you know that you can, with a key, there is always the reference which you might follow to get to the data. So we don't include those data parts in our pictures because it will not help to explain the tree. So that was notion number 1. Number 2 is more or less what they say in on the slide. They say you've got some keys. There are zillions of various keys, and they are organized into this shape with one key at the top, which is called the root of the tree, quite obviously. It also contains some key, and then the rule, which is the basic rule of any search tree, says if you go to the left from particular node, you will find only smaller values of keys. And if you go to the right, you will always find only bigger values of keys. And that holds for any node you might imagine. You may yourself check that it holds. If, for example, there is 13, to the left are smaller values, to the right are bigger values. If you now perform an in-order traversal of the search tree, and you print out all the values in that in-order order, then you will get the sorted sequence. So when you look at this tree from left to right, you will see sorted sequence. So the tree is just this part at the top. This what is here at the bottom just shows you, reminds you how it is organized there. Okay, so this is a search tree, and now that search tree is dynamic. We can insert new values into this tree. We can remove some values, I mean remove some keys, insert new keys, of course with their references to the data, or add the keys or remove the keys, and still the search tree will be in full, will be operative all the time. So let's see what can we say about it a little bit more. First of all, the tree is not that much regular. It looks, and it will be mostly relatively chaotic, as you see here. It is not regular. That is, some nodes have two children. Some nodes have only one children. We cannot do anything about it. It is not balanced. That's the most important fact about it. It is not balanced. So if you go into one direction and then you move into one direction, you might find leaves which are in very different depths. So typically what might easily happen, that you have one rather short branch, and then suddenly there are longer branches somewhere else, so it looks like this. So this system is, as you can see, far from balanced, which means that when you are going, following some path, when searching for some element, for some key which is somewhere deep in the tree, you have to go through many other nodes, so you spend significant time by searching. And in other cases, when you are looking for something else, which might be close to the top, typically, so then you spend quite short time. So this imbalance is an annoying part of binary search tree. And next week we will we will fix the problem that the standard binary search tree is not balanced. So we will try to balance the tree, but only next week. We can the three most important operations in any search system are there: find something, insert new value, insert new key with the data, and delete the information from the tree. So let's one by one look on them, how they work. First of all, they again tell us something about implementation. Well, all right, why not? Let's see what the implementation says. The tree, which is schematically here, is just some part of some tree, consists of nodes and edges. Edges typically point to the left and to the right child. That is to the root of the left and right subtree of a particular node, and you have, of course, to store the key. And again, we do not store the reference, we do not show the reference to the data, which in real life applications must be there. So what you have, a constructor says that when you create a new node in the tree, you typically initialize it by nothing on the left and on the right, but the key you store there in that newly created node. That would be it. Typically, when you have this class of nodes, you then need some structure for the binary tree. as a whole itself, and that is relatively easy again, because you might say, okay, all we need is a reference to some node, to some root. When you've got the tree, so if you reference to the root, then by, of course, traversing the tree downwards, you can access all other values. So it is enough when talking about your tree, just have a reference to the root, and that's it. You don't need anything more. So it is strangely enough, your tree is very big, and all you need is just one reference, and whole tree is accessible, which is, let's say, fine. So let's go searching. Let's go searching. How do you search for an element in the tree? First rule says, because your tree is accessible only by the root, so you have to start always in the root, and then you just take the value you are looking for, that key, and compare that value with the key in the node you are currently looking at. So you say, oh, 18, compare it with 51. And first of all, because you are searching, you probably will ask, is 18 equal to 51? So it is not. So then, is it smaller or bigger? Well, in this case, 18 is smaller, so you go to the left subtree, because you know that in the right subtree there are only values bigger than 51, so 18 cannot be possibly in the right subtree. So you go into the left subtree, you arrive into another node where the whole stuff recursively and literally repeats itself. 34, 18 is smaller than 34, so go to the left. 18 is bigger than 13, so go right. It must be in this subtree. Now you arrive to 22. 18 is smaller than 22. You arrive in some node. Well, 18 is there. You have found it, and you can now return the reference to that node. Or because we know that there is a reference to the data in the node, you can return the reference to the data associated with number 18 or whatever you want to do. So you have to go left and right, so you have to find your way in the tree. Unfortunately, that's very easy to implement, because here in the body of the function, what they say, while true, I apologize for these for these brackets, which are not necessary. So obviously this was a transfer from some Java or C++ code. I hope that does not matter. So while true, what you do infinitely, if your reference, what you are looking at, is none, if nothing, then you of course return nothing. Nothing was found. You cannot find it. If the key you are looking for is the same as the key stored in that particular node to which you are currently pointing, then you return the reference. In this case, they return the reference to the whole node. And otherwise, there are only two options. Either you have to go left or go to the left subtree or go to the right subtree. You can see that it is important to be aware of the fact that, for example, let's say there is 17, there is 22, there is 60. So when you are looking for, I don't know, or looking for 12, if you are looking for 12, you arrive to the root, and then you go to the left. And in 17, there is no reference to the left. That is, it's an empty reference. There is a reference to null or to none, however you call it. So when you are looking for 12, you go to the left, even if there is another reference. So you follow that null reference here. They say if the key is no smaller than node key, is 12 smaller than 17? Yes, it is. So go to the left, even if it is if you go literally nowhere, because just in the next loop you immediately ask whether current node is none. Yes, well, here we are in nowhere. So that means we did not find the stuff. So that's how it is done. So rather simple. In each node you make just 1, 2, 3. 3 comparisons, and that's it. So that's relatively, as you can see, efficient. Here is the same, absolutely same stuff done recursively this time, and you can see that the code is very much analogous to the previous one. If what you are looking at is none, then you return none, obviously. If you are in there, you confirm it by returning a reference to the particular node, and then you go either to the left, either to the right. What does that mean? That you just call find method on your key, and of course give them reference to the left or to the right subtree, and that's it. So finding anything in any search tree is relatively easy. Then come the operation insert, and then come the operation delete. And the operation delete is typically a little bit more annoying than the other ones, so we'll see that. Now let's go inserting. How do you insert? First of all, if you are inserting a new value, a new key into the search tree, then in fact it holds that there is only one position in that tree where that new element could be stored. You cannot store it, for example, when you are inserting 42, you cannot insert it into the right subtree of the root because 42 is smaller than 51, so it cannot be stored in the right subtree. Therefore, it must be stored in the left subtree of 51. All right, but then there is some root of that left subtree. That root contains key 34, and because 42 is bigger than 34, it must be stored in the right subtree of 34, and therefore recursively you go down until you locate exactly the place where 42 should be, if it's there, and then what you say is all right. So in fact, to insert an element means find the place where, go just searching for it in the tree. Finding 42 is simple, so you find the place and then you create a new node and just append it to the tree at that position. Therefore, we've got immediately the implementation, which looks terribly long, but I assure you that it isn't long, because there are, again, you have to also take care of small corner cases. Like, for example, if your tree is still empty, so there's nothing to search. So if your tree is empty, then you have to store your key, create a node, and set it to be the root, and then you return the reference to the newly created root, for example, and maybe you do some more initializations. That depends on your approach. Again, this semicolon might be forgotten. If the tree is not empty, what you do is then you have to find the place. So what you do, if you find that key you are looking at, if you find it already in the tree, you again return none. So that's another important property of the search tree, which I haven't mentioned yet, that you suppose when you are manipulating some data that your data are distinguished by the IDs and by keys which are unique, and that is reflected typically in your search tree. You don't store duplicate values in a search tree because you don't know where would you store them. And another 22 comes, and you have somehow to explode this node. Well, in principle, it is possible, but it is not a standard way. So no duplicates in your search tree, please. Otherwise, you either go to the left, either you go to the right. So if to the left you see none, if key is smaller than the node key, so if you have to go to the left, so you try to go to the left, but on the left there might be nothing. So like, for example, in this case, a nice case here. So if they say that is that null, if they say insert 12, insert 12, so you come to 17 and look to the left. You have to go to finding 12, you have to go to the left when you are in 17, but there is a null reference. So you first check that the reference, if there is none. So in that case, you have to create pop this 12 here. So 12 should somehow appear suddenly out of the blue at this position, new node, and there is your new node, and then of course this reference has to be set from 17 to from node width 17 to node width 12. You have to set this reference. It is done exactly here. Node. This is node. So node to the left is our new node, and that's it. Otherwise, if to the left there is something like when we started with inserted in 12, you come to a node, it has to be to the left of 60. So then you just go there. The node, current node, becomes the node on the left. Of course, the mirror case is when you are on the right side. If you want to insert something into the right subtree, so you can see that this lower part is exactly the same as this upper part. Only left and right are swapped. So that's it. So that it is, and this runs in the infinite loop, which of course after some time you arrive to the end of your tour through the tree, and there you have to insert your element, and that you must of course encounter this return statement. So that's done iteratively. Recursively, recursion is often much better in expressing the idea and helps keeping your implementation better, readably, more tidy. So what you do now again is exactly the same stuff. If you see the key you are to insert, you just don't do anything, refuse to insert it, and otherwise you either go to the you have to go either to the left with your key or to the right, and again there you check those if whether left exists. So if it does not exist to the left, if there is nothing here, so what you do is create that node. Otherwise you continue with inserting, and what you give them, of course, the reference to the node on the left. So that's the same stuff. The call again checks whether the root exists at all. If it does not exist, then they create a new root, and otherwise they continue with inserting the node into a tree which already has some data in it, at least one node. So that's it. Operation insert is easy. Next slide reminds us that while we know that the order of elements in the search tree from the left to the right is increasing, smaller, bigger, and bigger. The shape of the tree might be quite different. So this example shows you a sequence of insertions. You've got elements from 10, 20, 30, 40, 50, 60, 70. 7 elements which you insert into originally empty tree in this particular order, and the result is search tree which looks like this. If on the other hand you choose to excuse me. If on the other hand you choose a different order of the inserted elements, this is this one. Sorry, I don't This does not seem to be reacting nicely to my... So we had this example. If you choose a different order of the same elements, you might arrive at totally different arrays. So for example, here they inserted 40, 60, 50, 20, 70, 30, 10. So let's do it once more, but in reverse order as a simple exercise and see what we get. Just to get used to our search trees. This is impossible to wipe. So if we start at let us start at the end. So insert 10, you put 10 into the tree, then let's insert 20, 30. So 30 has to go to the right, then you go 70, 70 should go to the right of 30, then inserting 20, it has to be right of 10 and left of 30, so there is 20. Next in reverse order is 50, bigger than 10, bigger than 30, go to the right, 50 is smaller than 70, so 50 should be down there. It's 5, 50, 60, bigger than 10, bigger than 30, smaller than 70 and bigger than 50, so 60 should go down there. And finally 40, 40 should be sitting down there, bigger than 30 and smaller than 70 and smaller than 50. So you arrive into the tree which is here, and which is of course for searching less suitable, because for some values you have to go deep in the tree, while that one by chance is nicely balanced. So and more or less it is obvious that if they give you the same values in order 10, 20, 30 and so forth, 60, 70, so your a binary search tree would be rather completely degenerate, and so on, 60, 70. Such search tree is completely useless because you have to, it's in fact just one single list, and if you want to search in it for anything, it's the same as searching in a list, and that, as we know, is quite inefficient. So it is enough that when you are building a tree, somebody gives you a long list which is sorted. They want to help you. They say, oh, I give it to you sorted, and you can easily search in it. And you put it in a search tree, then it's quite worthless. Next week we will fix this problem effectively. Now let's go into deleting. Typically, deleting is most annoying part of any search tree. There are zillions of various search trees, and always deleting is problematic, mainly because when you are inserting into the leaves. That is the nodes which are somewhere on the fringes, and they are not inside the tree. You don't insert anything inside. You always insert at the bottom of the tree under some existing leaf. On the other hand, when you go deleting, they may ask you to delete the root or anything inside, not just the leaves. And that means that suddenly, when you just delete a node and forget about it, you lose the connection to the rest of the tree. And of course, now that node typically contains some fork, so you cannot just say, well, append one of the subtree to the previous parent, because then you would lose the other part, obviously. So that's a problem in most search tree. This is a problem. So those operations are typically most complex, and then exactly as we will see now, divide into more cases. So let's go into those cases. So whenever we have to delete anything in the tree, we do the following. We say delete, what do we have to delete? Something, I don't know, some value. And it turns out that that value is sitting in the leaf. So the node has 0 children. So that's case 1, because that is easy. You just say, all right, just remove the node. How do you remove the node? When you are searching for that node which you are going to delete, typically you have 2 options. Typically you have 2 options. There are always zillions of options in any. So the more complex the search tree, the more options there are. So there is not just any, we don't meet, sometimes we meet some golden standards, sometimes there are no golden standards. So deleting a leaf. So there is your 24, 17, and 30 there. So if you want to delete 17, you have to destroy a reference from 24 to 17. So variant A is, while searching for 17, when you want to delete it, you first must find it. While searching, while searching for the key to be deleted, keep the reference to the current parent, of the current node. Of the current node, so I will make it even bigger. What was there with 24, so that was, could that be, like, for example, 8 in there? And this is again part of some bigger tree. There is 70 up there. So while we are going down the tree and looking for our node, we also keep the reference to the parent. So when we start, we have our node here, and the parent does not exist. So parent is now of or none or anything like that. Then we move to the left because we are searching for 17. So then this becomes parent, and this becomes a node. And then you move on to 24, and 24 becomes your node, and you keep your parent pointing to 8, and you just take a node and parent pair and move that pair down through the tree as you are looking for the key you have to delete. That's one option, and when you do that, of course, then when you delete the node, when you find the node, you just destroy the reference from 24 to the left. In this case, just set it to none. We will see it in the code. Variant B, another possibility is to keep in each node, a reference to to the parent, of course. So if each node knows who is their parent, so then when you don't have to remember the parents as you go through the tree. When you arrive to the node you have to delete, then you say, all right, look to the parent, aha, here is the parent, and then just then you are in the parent and destroy it. Obviously that takes some additional memory. And now memory. That takes some, but it's faster to process because you don't have to move 2 pointers as you move down through the tree. You just move 1 pointer. So it's typical trade-off. Depends on your situation, which approach suits you best. Whether you keep your tree as simple as possible, and then you have locally to do more work when you are in any of those functions, of those operations. Then you have to keep the track of more nodes in the tree, or everything is pre-stored in the tree. But again, then it works faster. It eats some memory. That mostly depends. So that it's easier. Remove the root, remove the leaf. That's easy. Now, in a search tree, there might be nodes which have only one child. Delete the key in a node with one child. All right, so if it has one child, it's still a relatively simple case because you can go and say, well, if this node disappears, then we just ask the parent to adopt as a children, not its children, which was there up to this point, but its, in fact, grandchild. So that is child 68 of 76. 73 is something like a grandchild. So, and there is only one of those. And because 73 is bigger than 68, but still it is in the left subtree of 76. So if you remove 68, then 73 and everything which is below will still be smaller, of course, than 76. So you can just adopt a new child of the parent of the node which is being deleted. So they say it here, and how do you do it? Simply as that. You just change this reference. Again, you don't, in this case, you don't have to, you still have to get to the parent. When you get to 68, they say you delete to 68, you get here. So then you again have to go to the parent. So both of these strategies are applicable. So again, you have to choose in advance which one will you, which one do you adopt and which one do you use. But then, of course, changing this one is easy. What happens to the node which has disappeared? The 68. Then nothing is pointing to 68, so it goes in some garbage in the memory, and you might hope that garbage collector takes care of the node which has been deleted and does and frees the memory. So if you are in a language which relies on garbage collection like Java or Python, then you just change the reference. If you are in C or C++ or that kind of languages, then you have to take care yourself typically, or it is better to take yourself care, and you might also want to destroy that reference manually. There is also a possibility not to rely on objects and store the whole tree in system of arrays where you take care of absolutely everything, and sometimes it is faster, but I will leave that for practices if time allows. So removing node with one child, not a big problem. Find the node and then just change the reference. Well, so here they give us before and after picture. 68 is gone, and you can see that everything has moved up, which was below that node. So that's simple. Oh, sorry. Sorry again. Now we arrive to case 3 when we have to delete a key in a node with 2 children. So they want us to delete 34. We cannot just remove and forget about that node because the left subtree of 51 is now broken itself into two different subtrees. So we have just to somehow to reorganize left subtree of 51. And what do they do is this. Take one of the subtrees of that unfortunate deleted node. You don't delete that node yet, so we know that we have just to remove 34. So you say, all right, take one of the subtrees, left or maybe right. In this case, we take left. Right is as good as the left one. The next example will show it. And in that subtree, you will look for the leftmost element. The leftmost element in that subtree is the smallest element in that subtree, like 36 in this case. So if we somehow transport 36 up to the node where we had that 34 to be deleted, then 36 again will work as a middle element between left and right subtree. Of course, 36 must be removed from the right subtree. And when that remains there, when that is removed, so 36 will be up there. And again, whoever is looking for 40, 38, 45, or any element in the left subtree of the whole root will be correctly sent to the left or right subtree of newly created 36 up there where 34 was originally. So that means that when deleting this 34, you cannot stop there. You have to go down in the right subtree and find the rightmost element there, because it is leftmost, and because it is leftmost, it cannot have 2 children. Why? Well, if it is leftmost, so if there is something to delete, there is your D to be deleted, then you go to the left subtree, and in that left subtree, you are looking for the leftmost element. Then, of course, that leftmost element cannot be an element with 2 children, because it would not be then leftmost. You still can move to the left. So the leftmost element is either a leaf, as shown there, either a node which has only, as in this case, which has only right a child. So in that case, you can say, aha, so there is the value which might be put up there as a substitution for the key which was deleted. So this value of S might go up instead of into the same node. And then you say, aha, and then go and delete the whole node, which we already know how to do. We just, it's a node with 1 child, so that can be easily deleted by changing the reference from its parent to its own child. So now we can, in these 2 steps, we can delete 34. And that's probably it. No, that is before. This does not show what I wanted to show. So I have to update it a little bit after. This is not the picture which belongs there. Obviously, it's something else. Now this one is correct. 34 was deleted, substituted by 33. So this node completely disappeared, and 36, is living now up there in originally node which originally contained 34. So there it is. Now there is another alternative approach to the problem, which says, okay, we don't want to shift the values from one node to the other. We don't want to remove the key from the node and put it into the node. Maybe for some reasons, a key which is once it is in the node, then it sits in that node. It cannot be moved out of the node anywhere. So in that case, you say, okay, you can do the same manipulations with the nodes only. The values, the keys remain in the nodes, and you say, okay, we remove this whole node 34 with its key. It will disappear from the tree, and now we reset all other references so that it is 36. The whole node of 36 will take a role of which originally had the node containing 34. So what? After finding the node X with the key to be deleted, find a leftmost node in the right subtree of X. That is this one Y. Then point from Y to the children of X. So far it had no children. So now this blue line say, okay, now 36 adopts new children. From the parent of Y point to null, 38 loses the whole node 36 as their own children. And from the parent of X, which is 51, point to Y, point to 36 now there. So at this moment, when those dotted line connections disappear and the new blue ones are introduced, then the whole node Y simply suddenly assumes the role of the node with 34 as before. So again, you might choose yourself how do you want to implement your stuff, just by manipulating the pointers or transferring the contents of the nodes from one node to another node. Now there's the example. Yeah, there is the example when the node which is substituting the deleted key has some child. You can see that we can also use the rightmost node in the left subtree. The left subtree of X locate with the biggest key. Yeah, so that is here again. 22 is the closest value to 34. Which is smaller than 34, so that's closest again, so it will divide again a left and right subtree of original 34 into smaller and bigger values correctly. So you do the same stuff as we did before using this 22, so that's easy. And oh wow, we've got only 5 minutes, and very probably we are at the end of the stuff, because now we can do delete in all possible cases. So therefore, this is before and after. 34, we just took 22 and it went up, and here again between 13 and 18, it is not sitting there anymore. Now, okay, alternative approach is exactly the same, so I don't have to comment on it too much. You can see that again we reset the new pointers, and the old ones are forgotten. 1, 2, 3, 4, 5 relations at most are destroyed, and instead of them we have how many? We have 4 new relations. So, and that's it. Each is again either represented just one pointer down, or maybe also everybody is pointing out to their parent. That again depends. So let's see the implementation very briefly of delete. What do they say? Well, it looks long. There are 2 slides, so I'll try to comment them in 3 minutes, I hope, which maybe is not that difficult. So the delete we do, we again adopt the approach that we register node and the parent. So we move through the tree registering a node and parent. And again, we first have to find a tree, so we either go to the left or to the right before we find that node to be deleted. And when we find it, then again we look. If we are in the node which has both children, then we call function find minimum in the right subtree. There is a suitable picture here. Find minimum in the right subtree. That's another function which returns reference to the smallest node in the left subtree. And then we just do what we do. First of all, the keys, we take this key and put it into current node, which the key which was found in the right subtree in the smallest, that's the smallest one in that right subtree. And then we apply the delete node with at most one child to the node which was found. It was found in the right minimum node, and of course also remember their parent. If on the other hand the node which we have found was not a node with both children, then we have somewhere the function which says delete node with at most one child, which is exactly the same as here, and that one is on the next slide. And again, what do they say? Delete node with at most one child. Well, again, they look either to the left, either to the right, and of course then just they do the connection of parents. So here is the right child, case of left child, case of right child. So you can see that they are the same, only left and right are swapped. And that is the first case when the node has no right child and it has also no left child. So then we just go into the parent and set either left, either right, because node which has to be deleted. For example, if you deleted 17, so it is the left, so you have to decide whether you delete the left or right child of the parent, and that's in here. And the left child is just again resetting from parent to the child of the deleted node. So that's very easy, and finding minimum in the right subtree is very easy, because you would make one step to the right and then you go to the left as long as possible. While node left is none, so you go from node to so you go to the left as long as possible. So that's easy, and that's it. So you node left, and parent of course trails behind the node. So that's it. So the whole delete is on the previous slide. This is the read. Of course, obviously it is recursively. It is not that nice to implement it iteratively. So you cannot rely on recursive function completely, because if for some reasons your tree gets too deep, then the stack of recursion calls might overflow and it will not work. So maybe recursive. So non-recursive implementation in real life is maybe better. So the conclusion says typically our tree is not balanced. And in that case, all operation, in worst case, have to go to the very bottom of the tree, and there might be up to n steps, up to n nodes you have to go through. So your complexity is big. If the tree is balanced, which is, as you can see, no one can guarantee it, then you can perform any operation in time proportional to logarithm, because the depth of the tree is then logarithmic, and you spend only constant time as you move through the tree in each level. If a tree is randomly built, then it will be more or less nearly balanced. This will not happen if you change your key. If you choose your keys completely randomly and insert them into the tree in random order, or you choose them not randomly, you insert them in a completely random order, then you arrive at a tree which is nearly balanced, which is nice, but then again, no one what happens in subsequent insert and delete operations, how it becomes disbalanced or so. So if you work with totally random data, you might expect this performance, which, as we know, is fantastically efficient, but that is but how you have to really ensure that everything is random. So that's about it. Thank you. And during the seminars, we will look at some examples and try it ourselves. And next week, we will improve the search tree to keep it balanced all the time. So thanks for that.